Yeah, I'd like to welcome everyone to our session of the Fall Technical Conference webinar series. I'm Richard Warren. I'll be hosting the conference today. So just again, a little bit about the FTC. It's a conference that's sponsored by two different societies, and within those societies, two different divisions or sections. So ASQ and ASA. And yeah, you can get more information on the FTC here at the website below. So if you would save the date, we've got FTC coming up next fall. I'll be hosting that here in Park City, Utah. And again, that's mid-November in 2022. Hopefully, COVID will allow us to meet in person. We've had to cancel it for the last 2 years and have webinar series instead. So thanks, Sarah, for putting these together. The webinar series to keep us still kind of connected as a community. Okay, here's some of the upcoming webinars that we've got. Again, we're right here in the series. Next week we've got a couple of excellent speakers and talks coming up. So both Wednesday and Friday, I'd like to encourage you to come to those if you're able to. But yeah, today we'll be honoring Christine AndersonCook with the Gerry Hahn Award. She received this award, and it was given to those who, again, demonstrate outstanding achievement in quality and productivity over a sustained period of time. And it's named after Gerry Hahn, who definitely exemplified these traits over his career. And so I'd like to give a quick introduction to Christine. So she's our honoree and our guest speaker today. She recently retired from working as a research scientist in the Statistical Sciences group at Los Alamos National Laboratory. She was a contributor to more than 80 projects at Los Alamos, and before joining the group there, she was a faculty member in the statistics department at Virginia Tech. Her research interests include design of experiments, response surface methodology, graphical methods, reliability, multiple criterion optimization, and data-centric decision-making. She's a fellow of the ASA and ASQ. She served on the editorial boards of Technometrics, JQT, QREI, Quality Engineering, and the Journal of Statistics Education. She's a longtime Statistics Spotlight Roundtable column contributor in Quality Progress. She's received the 2012 William G. Hunter Award, the 2018 Shewhart Medal, and received the George Box Medal in 2021. And of course, she's this year's recipient of the Gerry Hahn Award. So I'd like to warmly welcome our guest speaker, Christine AndersonCook, and warmly congratulate her on this achievement. So I'll turn the time over to her just by way of, I guess, format. So I'll be monitoring the questions. You can put those in the Q&A box, but I'll be holding those until the end of the presentation. So I'll stop sharing now, and Christine, I'll let you share your screen.
Thanks, Rich. Let me just, having a tough time multitasking. So does that all look good in terms of presentation mode? Great.
Yeah, we can see it great.
Thank you. So thanks for the introduction. And it's indeed a big honor to be receiving this award and to be able to talk to you today. So I'm going to talk a little bit about practical necessity and how the needs of our science and engineering colleagues can help us figure out where statistical innovation is needed. And so first, I'd like to also give a big shout out to Lulu. She was a postdoc of mine at Los Alamos many years ago, and now she's at the University of South Florida. And as you'll see, we've collaborated on a lot of different projects, and she was the one who put together the nomination package for me. So thanks to Lou. Before we start, a little bit about Gerry. So I was very fortunate early in my career to be able to overlap with Gerry at some conferences, and I've certainly looked at a number of his books. And And so I think some of the things that I associate with Gerry, some of his hallmarks that you can see in his books and also that I remember from conferences, is that, you know, he was really quick to see what's important and he could articulate it very clearly to help others to see a good path forward. And so I think those are things that we can all strive to emulate as well as Gerry did them as we communicate in the broader statistics and science and engineering communities. So Gerry is one of my heroes in terms of how well he's able to communicate to the broader community. All right, I'm going to talk a little bit about some of the transitions that I've made in my career. And so I'll just fill in a few details about sort of the path that I took to get here. So I graduated in 1994 and I was a Jeff Wu student at the University of Waterloo. And I feel like that really helped me build a solid foundation for just expertise in design of experiments, but also applied statistics in general. And then I had 10 years at 2 different universities as a faculty member before transitioning in 2004 to Los Alamos National Laboratory, where I spent the rest of my career as a research scientist in a very collaborative environment. And I do feel very privileged that my career, I think it's spanned some really exciting times in statistics. And so they provide a backdrop for a lot of things that I've thought about and worked on in the course of my career. So the first one is, I think, if we look back to 1994, the state of graphics was very, very different. And so I think graphics to me represent a huge opportunity for us as statisticians as a vehicle for communication. And so I'm very happy for the innovations that have happened in the span of that last 27 years. I think there's a renaissance of design of experiments. When I was starting off and my dissertation was about design and analysis of experiments, people were saying that all the interesting problems in design had already been solved. And so happily they were very wrong. And I still feel like there's emerging problems in design of experiments that need statisticians to weigh in and offer good solutions. And I'll talk quite a bit about things related to design of experiments because that's where I've done a lot of my collaborations in that space. There's been a dramatic increase in computational power all around, but particularly in algorithmic searches, both for analyses and also helpful for design. And so I think that's a nice backdrop of just a lot of things that we could only dream about doing 20 or 30 years ago now are something that's quite accessible. The dawn of data science or big data, lots of buzzwords, but who would have dreamt at the start of my career that we were the cool kids in class, that we had a set of skills that were highly desirable and becoming central to how problems were tackled and solved. And then lastly, statistical engineering, which was formally introduced by Roger Hurrell and Ron Snee in 2010, that has evolved into the International Statistical Engineering Association. And so I think the practice of statistics is something that's much more front and center. And I view that as something that's tremendously powerful and very exciting for us as statisticians. I'm reminded of a quote that my first department head, David Bellhouse, said to me many years ago. If you're lucky, you might have a handful of ideas in your career that really have a broader impact. And the profession needs both explorers and settlers. And so I think this has resonated with me throughout my career. I think a lot of times as we graduate from our statistical studies, we're given the impression that we should all be explorers, that we should be discovering and developing new methods. But if you think about the role of the settlers, they come behind the explorers and they turn those ideas and methods into something that's productive and fertile and enables benefit to society. And so I think as I reflect on my career, I think that I've made more contributions as a settler, and only a few ideas have fit in the explorer category. But I think there's tremendous value in both of these aspects and that we should embrace both of them. So as I said, this will be a bit of a reflection of sort of an important transition that happened in my career. And so it's all about my role as a statistician in collaborations. So early on, I think it's not a bad parallel to say that I operated a little bit like a sales clerk, maybe in a hardware store. The customer comes in with a problem. You take the description, you go to the right shelf and find the right product to solve their problem, and then send them on their way until they have another problem. So in a design of experiments context, this might look like they want some help collecting data. You go and find the right design to match their needs, and then off they go until they return, maybe with help for the analysis. So this is productive. Hardware stores aren't going anywhere. So I think this is a good way to start. But where I operated in the last 10 or more years of my career looked more as a parallel to something that might be an interior designer. So you meet the customers in their space. So you're building a much deeper context for what they're trying to do. After understanding what's important to them, offer several possibilities. So in the case of a designed experiment, maybe offer several different designs, sit down and talk with them about what they like and dislike about each of those choices, so that you're developing a deeper understanding of their priorities and the context, and also helping them understand what they like and need. And then we iterate through this until everyone is satisfied with the final choice. And the experimenter in this case makes a choice about what the design is that should be run. So what are the key differences between sort of the start of my career and how I was thinking and how I finished up? Well, I think it's a much more team environment when we're working collaboratively. And I think we have a deeper understanding of, number one, what looks like the right solution, because we've defined the problem much more carefully. There's also this notion of multiple options being discussed and compared. And I think that will be a central theme about a lot of things that I talk about today. And there's an iterative nature to this. And so I try to convey to experimenters that creating the designs, the role of the statistician, is relatively easy compared to executing the experiment. So I want them to feel really comfortable to say, well, I like this, but I don't like this. And so that they feel free to sort of help shape the direction that the design is going. And the experimenter, of course, owns that final decision. So what are some of the advantages of this approach? Well, for the organization, it should be clear that the class of problems that we can tackle and solve is much bigger if we sit down as a team and use the collective wisdom of the entire group to tackle the problem. I think we have better definitions of the problem, and therefore we can get to better solutions. And the collaborators, our scientists and engineering colleagues, feel much more ownership of the statistical part of the solution. And the collaborators also are sort of learning some statistical thinking ideas that they can use in other projects. So they're learning things just as we're learning things about their background and their application. It's also very good for the statistician. I think we have the potential to contribute to much larger impact problems. It creates a pull for the involvement in subsequent projects. I feel for the last 10 years, I wasn't doing a lot of convincing of people that they should be running experiments, but rather they had seen successes on early projects. And so we're coming back wanting that kind of success and that kind of improvement in their data collection because they had seen it in action before. I think statisticians sort of become full members of the team. We're not sort of in the technical support category, but we're sort of viewed as key contributors. And all of that really has the potential to give us greater professional fulfillment. So that's sort of the end game that we're striving for here. And the way that I'll talk about this is how do we transition from that starting point of the sales clerk to someone who's an integrated part of the team. And so I identified 4 needs that I I worked to tackle, and then the innovation associated with them. So the first need was a richer set of tools to be able to compare designs. And so the innovation that I was a part of was part of Alia Zarain, the picture on the left-hand side. Her dissertation included fraction of design space plots. And many of you will recognize the picture there of Ray Myers, who was also on that committee. The second need is the ability to handle multifaceted goals. And in my experience, a lot of unexpected things happen with data collection. And so being able to incorporate that into our designs, Pareto fronts, where we get to specify what the criteria look like. That was a contribution made with Lulu and Tim Robinson, who's at the University of Wyoming. The third need that I'll talk about is the ability to hedge our risk from a lack of knowledge. A lot of times when we're starting to design our experiment, we don't know a lot. And so if we can sort of hedge our bets a little bit and learn and leverage as we go, then sequential design of experiments can be very important. And this is a concept that's been around for a long time, but I think it's vastly underutilized in practice. And so Lou and Tofig Ahmed and I have developed some infrastructure on that space. The fourth need involves improving our structure for team discussions and decision-making. So being that team member as part of a collaborative team. And so there's a couple of ideas there. Structured problem-solving approach called DEMREX, collaboration and graphical tools. And so Lou and Pete Parker at NASA Langley are involved in that. So that's our journey for today, to walk through these 4 different needs and some contributions that I've been a part of that I think have helped move the needle a little bit in these spaces. So need number 1, tools for comparing designs. So I think we make better decisions if we have a variety of choices. And so I seem to be stuck on a hardware theme here today, but imagine that you need a mousetrap and you walk into a store and it has exactly one kind of mousetrap. Well, the decision's quite binary. You buy it or you don't. But now imagine that we are faced with a shelf that has multiple different mousetraps on it. I think the whole nature of our thought process changes. As soon as we have choices, we become much more engaged. We think about which of these is the right solution for my problem. And we can evaluate and compare their differences when we have this richness of space for comparing things. And so our goal here is to have graphical or numerical summaries that match what we're trying to accomplish with our experiment. And that will allow us to compare designs more effectively. So we're going to do a little bit of time travel. The fraction of design space plots were created around the year 2000. And the goal is to compare how well different designs predict throughout the input space. So I think this is a pretty typical use of the models and analyses that come out of designed experiments, where we're going to use that model to predict what the response might be at different locations in the input space. One of the tools that was out there at that point in time were the single number design diagnostics. So G and I efficiency tackle various aspects of prediction variance, the worst case and the average. And if you think about a multi-dimensional input space, a single number is probably a bit too simplistic for understanding that performance. And we're not going to be using the model to predict at an average or worst location. We're going to instead be trying to use it at multiple input locations. So helpful, but I think a little bit of a blunt instrument to help us understand designs. Another tool that was out there was a variance dispersion graph. And so this was designed for a spherical region. And so the x-axis goes from the center of that circle or sphere out to the outer edge of the design. And we have a curve to compare the different designs. And so here we're looking at 3 different designs that we're comparing in a 2-dimensional space. Well, The problem is if I'm looking at a two-dimensional space or a three-dimensional space, the amount of area or volume that's at the center of my circle or sphere changes as I change the dimensions. So it's hard to think in general terms about where I should be looking and how much emphasis I should be putting at different locations on that curve. It's designed for a spherical region. A lot of times we don't have that. And what I've shown on the plot on the right is actually a simplified version. There could be 3 lines for each design. And so it's really hard to know what we're trying to do in terms of this comparison. It's providing helpful information, probably better than the single number summary, but it still is quite confusing, and conveying what this plot is all about to a non-statistician is quite confusing. So the fraction of design space plot is a single line for each design. It doesn't matter the dimension or the shape of the region. And what we're comparing actually is, I think, a lot more natural. So it's really just a cumulative plot of the prediction variance. So the x-axis here tells us what proportion of the distribution of prediction variances we're looking at. And so the left-hand side tells us the best, the right-hand side tells us the worst prediction variance, and we can pull off any fraction that we like to see what proportion of the prediction variance is at or below that particular value. Bonus, it's easy to generate, which I think is very helpful. And over the years, this has been adapted so that it can help us answer other design questions as well. We can compare designs of different sizes. If we're not sure about the model, we can do a fraction of design space curve for each model for a particular design. And if we're looking at generalized linear models, which are dependent on the model parameter values that we choose, we can have a curve for different parameter values. And so lots of extensions that allow us to explore different aspects of the design, depending on what's important to us. Fast forward to today, I think the whole comparing designs has become much more central to the way that we evaluate things. We have those single number summaries. We have the ability to look at estimating the correlations between individual terms in our model. And then we also have some tools for being able to look at that prediction variance and how we're performing throughout the input space. So very rich collection of tools that are now available and easy to access that allow us to look at several designs and really understand them. So what does the process look like for me when I'm helping a team plan data collection or an experiment? I think we begin with a detailed discussion about priorities. What does success and failure look like? And then we create designs that are sort of start with something and then be responsive to new information. And creating new designs is not hard in the era that we live in. And so that's a real luxury. Using graphical methods, we can present several alternatives with their advantages and disadvantages. And then we let the experimenter make the final choice of design between those sensible alternatives that we've already curated. So we're not presenting them with a choice that doesn't feel like a good choice, and then they're able to own that final choice. I think that leads to much greater comfort than, hey, trust me, I'm a statistician. I know what the right design is for you. And I think it also gives a better chance for the experimenter really being committed to the implementation going successfully. Okay, the second need is the ability to handle multifaceted goals. And one of those goals is to protect from things going in an unexpected direction. And so Pareto fronts give us that flexibility. This is one of my favorite pages from the Response Surface Methodology book with Ray Myers and Doug Montgomery. And it outlines a number of potential goals that we might have for our experiment. And far and away, the optimality community has focused on that first category. So for a chosen model, can we get good estimation of the model parameters? And can we get good prediction throughout the input space? But I think beyond that, we often have other objectives that should be in play as well. So we're making assumptions about the model and other things, so we should be able to test those. We want to have on our radar protection if things go badly. We want implementation flexibility, and then cost is always at play here. A bigger design will always allow us to do better in any of these categories if we prioritize them. And so I think my hesitation with optimal designs is that optimal is conditional on two quite big assumptions. So one, it's dependent on our choice of model, and we might not get that right. And two, it's conditional on the experiment being executed the way it was planned. And so I think we want to actively think about how confident we are in those two assumptions. In addition, we often seek to squeeze more out of each experiment. And so we may be trying to accomplish more than one thing. And so the ability to have more than one criterion in play is very helpful. So Pareto fronts are a very useful tool for tackling this. And so for those of you who might not have seen a Pareto front before, I'll walk through some basics in the context of a new class of space filling designs called input response space filling designs. So if you tuned in to Rashawn Joseph's talk on Wednesday of this week, he talked about some space filling designs using a criterion called maxi-min, where the goal is to space the design points as far away from each other as possible in the input space. And so here is a 10-run design with 2 input factors, and the green dots correspond to the design that we're looking at. Well, if in addition to that, I am interested in how the responses will be spread out once I collect the data, here is a complementary plot to that. So the gray histogram underneath corresponds to the values that we have in the contour plots on the left-hand plot. And so we're expecting to get values between 40 and 50. And so perhaps one of my goals is to get good spread across the range of the response values that I anticipate. And so I'm going to add that as a second criteria here on the y-axis. And I'm going to build a Pareto front that focuses on those two objectives. So ideally, these are both maximized criterion. So we'd like to operate in this top right corner. And so the Pareto front gives us the set of solutions that is at that leading edge towards our desired corner. There are tens of thousands of other designs that we could construct for our 2-factor 10-run design. And the advantage of the Pareto front is it allows us to throw away almost all of them as non-contenders. We only need to think about the Pareto front as the set of solutions to explore. It includes the best of one criteria, and it also includes the best of the other criteria at the other end. So here is the best response-only space-filling design. And you can see that those purple lines that correspond to the 10 design points are now beautifully spaced between 40 and 50. What's not so great about this design is how it looks in the input space, where I've got some bunching up of design points and I've got some big open spaces. And so the Pareto front gives us an opportunity to sort of slide along between those two extremes and see what kinds of designs are possible that sort of get an appropriate balance between the two objectives. And so if you go from left to right or top to bottom on the Pareto front, what you're doing is sliding your emphasis from response only to a balance where ultimately we end up with input only. And so this hands over control to the experimenter so that they can see several alternatives, evaluate their pluses and minuses, and select what balance makes the most sense for them. So we're back in this space of having the active engagement of the experimenter about which choice makes the most sense for them. The beauty of a Pareto front is that it's pretty easy to adapt this to any scenario where we're able to get quantitative summaries of our objectives. And so in the literature, we've explored a number of different scenarios where we get to pick and choose which criterion to look at, and then build a Pareto Front and use some graphical tools to compare those options to choose a best design for our scenario. So what has experience taught me? One, getting the model right before we collect data is not that easy. And so it's nice if we're not entirely tied to having that decision turn out well. Different stakeholders have different priorities for the experiment. And so the Pareto Front allows us to accommodate multiple ideas and priorities very easily. And a close to optimal design that can survive some surprises, to me, is so much better than a non-robust optimal design. And so Pareto Fronts allow us to specify those priorities. For each situation, we get to adaptively choose what we're focusing on. It presents us with multiple designs that we can create and compare. And we have graphical tools that allow us to discuss the alternatives. And we can see how severe the trade-offs are for the priorities that we've chosen. So the green, orange, and red lines correspond to different shapes of Pareto Fronts that we might encounter, where the green curve says, okay, you can get close to optimal on both criteria that you're chasing. The orange line says you're going to need to make a commensurate sacrifice to improve one criterion. You have to sacrifice on the other. And sometimes we get unlucky, and that red curve says that there's a very sharp contrast and sharp trade-off between our criteria. But I think we're better off understanding how sharp that trade-off is, and it allows us to build in some intentional protection if things don't go correctly. Okay, so we have the ability to compare designs. We have the ability to construct a suite of designs that give us a variety of ways of valuing our different objectives. And so now let's switch gears to acknowledging that a lot of times when we set out to design an experiment, we don't know that much. And so if we can adopt a learn and leverage approach, then I think we're going to be in better shape. And so sequential design of experiments and another new class of space-filling designs called non-uniform space-filling designs are two tools that I think can help us in this category. So sequential design of experiments, my analogy here is if you're going on a long trip, before you step out the door the first time, do you want to commit street by street to the entire journey? Or would you like to know what the final destination is, but plan a sensible first day? And then at the end of that day, say, well, you know, traffic was bad. I'm not feeling so high energy. The weather looks bad. Let me update what I think I want to accomplish tomorrow, and sort of progress on the journey in those increments. And so I think we can do that with data collection. We shouldn't be thinking about committing our entire experimental budget right at the beginning, but we want to instead learn as we go. One tool for that is a non-uniform space-filling design. So if we're going to learn in the first stage, we need to have tools that allow us to incorporate that knowledge. And so most space-filling designs are predicated on having the same emphasis throughout the entire input space. But what if we gave the experimenter an easy tool so that they could say, I want to prioritize this region more and prioritize other regions less? And so the contours here correspond to a user-provided sort of desirability score for how much we want to emphasize some regions over others. And then you can see we've built a space-filling design that actually emphasizes the more desirable region at the top of this contour mountain more than down the slopes. All right, sequential design of experiments. I think Sir Ronald Fisher, when he started, he was working in an agricultural environment where you decided on the input factors, you waited an entire growing season, and only then did you get feedback on how things were going. So this is not a good situation for sequential design of experiments. But in a lot of business and industrial applications, we can collect, measure, and analyze the data in a very quick turnaround. And we often are working with processes that are stable and consistent over time. That's a desirable attribute in many experiments. And so there are lots of situations where we can tackle sequential design of experiments and use it to our advantage. When is it particularly advantageous? If there's uncertainty in the input region, we can avoid wasting resources by putting things in a space that we later decide are not useful. If we just don't know much about the process, then let's start small, learn something, and then figure out what it means and what we should do next. A lot of times there's natural constraints on timing, so we can only collect a certain amount of data in a day or a week. Those are natural stopping points where we can just take stock and figure out what we want to do in the next stage. I'm not suggesting prolonging the experimental timing, but just intentionally stopping a few times and taking stock of where we are. And then lastly, experiments have multiple objectives. And so if we can tackle those one at a time and leverage what we know, I think there's an opportunity there. So here is a common set of objectives that I've seen in lots of different problems. We often start with a pilot study where we can get quality data and we want to figure out if we can measure the responses that we need. Many times the experimenter might start these kinds of studies before a statistician gets involved. And then we want to do some exploration throughout the input space. So here we've got a space-filling design that takes into account sort of where the existing data already are. And we're trying to understand that relationship between the inputs and the responses. We might learn that a particular corner of the input space is not interesting or not viable. And so we can eliminate that from future data collection exercises. And we might do that exploration iteratively. Once we understand those basic trends and patterns, we might want to formalize our knowledge in a model and then refine that model. And so here we've collected 5 more observations where you can see that I've targeted regions that had higher uncertainty near the edges of my input space. And that allows me to refine the model and have more confidence in it. This again could be done iteratively with several stages, but at the end of this stage, we feel like we have a model that we can trust and we have confidence in. So using that model, we might identify a location that looks most promising for us in terms of the responses. And so we might do an optimization design, a more local design, collecting data near that optimum. And then finally finish with a confirmation experiment that verifies that what our model predicts we can actually achieve in practice for production or operational use. So you can see at each stage I had a different goal, and the nature of the data that I collected for that shifted as I progressed. So let's take a moment and compare how that looks relative to a one-shot experiment. So here is another one that had the same budget, 18 runs. And you can see that in the region that I later decided was not terribly interesting, that top right corner, I've used 4 of my 18 runs in that area just because I didn't know that it wasn't of interest. And then also the region where I ultimately want to operate, I just don't have any budget to feel precisely that I know what's going to happen at that optimum. So when it's possible, sequential design of experiments can offer us some big opportunities to really take maximum advantage of what our budget allows. So switching gears a little bit to the non-uniform space filling design. The idea here is that we're giving the experimenter control to emphasize some regions more than others. Well, how we define those weights really is going to shape how the design turns out. And so we want to assign bigger weights based on what our goals are. So if we're trying to optimize, then we might target response values that are looking better to us, assign those bigger weights. If we're in an exploration stage where the more interesting features are or where the response is changing more quickly, assign those bigger weights and we'll get a greater concentration of points there. If we're doing model refinement, we can set up those weights to correspond to regions where the prediction variance is large or the prediction interval is widest. And so we can target things based on what we're trying to accomplish. And then lastly, if it's a calibration experiment, we might want to target regions where the computer model and the observed data are most different from each other to really understand what our model is missing. So very flexible to adapt those weights to whatever we want them to be. Once we have the weights, what are we going to do with that? Well, for a lot of space filling designs, we're going to be using a distance matrix or a distance function where for a preliminary experiment, we're going to have the distance between all of the design points from each other. And typically that's just a Euclidean distance. If it's an augmented design, we're not only interested in how far the design points are from each other, but also how far apart are they from the original data that we already have in hand. So we're looking at more distances that we're trying to optimize. But for the non-uniform space filling design, here's how the weights get incorporated. So you can see that if I've got a small distance between 2 points, I can make that look larger, and so not something that I need to adjust away from if I associate that with bigger weights. So if something has a bigger weight, then I can in fact tolerate more points closely packed together for that combination. And so we're going to be able to tune the degree of non-uniformity by scaling those raw weights that we get from the experimenter into a range that goes from 1 up to something that we're calling the maximum weight ratio, where if the maximum weight ratio is 1, all the weights are 1 and it collapses down to a uniform space filling design. But as the maximum weight ratio increases, that allows us to tune the degree of non-uniformity that we're seeing. And so here are 3 designs as we go from left to right. You can see that for the same underlying weight structure given to us by the experimenter, we're starting to squeeze the design points in closer to the target of the most desirable region. And so again, this gives us an opportunity for the experimenter to look at several alternatives and pick the design that makes the most sense for how unbalanced they want that emphasis of regions to be. So how do we put together a sequence of experiments? Well, that's going to be different for most scenarios, but here are a couple of examples of how this might work. So for exploration, we might start with a uniform space filling design and then augment it with another uniform space filling design. Well, so how is that better than one big uniform space filling design? If in fact we've learned something from that first experiment, we might shift the region or change its size, make it bigger or smaller, or introduce a constraint if some region is not interesting. And so that second design gives us an opportunity to leverage what we've learned. A second case, if we're optimizing, we might start with a uniform space filling design just to build some basic knowledge, build a rudimentary model, and then use an augmented non-uniform space filling design where we've chosen those weights to be based on how much uncertainty we have about our predictions. So make it based on the width of our prediction interval. And then that will target new design points to be more likely placed in regions where we have the biggest uncertainty of prediction. Now we have a refined model that we have more confidence in, and so we can augment that again with another non-uniform space filling design, but this time we're going to specify the weights based on the responses where we're emphasizing locations where the response looks promising. So by using those weights in different ways, we can target different objectives. The third case is if we want good prediction throughout, we can start with a uniform space-filling design, and then maybe augment that with an input response space-filling design. So that's the one that I talked about in the Pareto Front section, where we're looking to balance and make sure we have good spacing in the input space and also good spacing across the range of responses that we've observed. So with a relatively small set of tools, we're able to cobble together a sequence of designs that makes the most sense for our particular problem. Okay, lastly, we want to improve the structure for team discussions and decision-making. And the spirit of this is that we're only as effective as statisticians when we can get our voices and our messages heard. And so here are a couple of ideas that I'll point to some work that we've done that really help in that sphere. And I think they all fit in under the umbrella of statistical engineering in terms of they're helping us with the practice of statistics and solving real problems. If you're a student of Six Sigma, you'll be familiar with the DMAIC process for structured problem solving. So define, measure, analyze, improve, and control. Well, Lou and I proposed a similar structured decision-making process: define, measure, reduce, combine, and select. And I'll walk through an example of that in a moment. And then using graphical tools to facilitate discussion and decision-making, and then some strategies for successful collaborations. So I think the whole space of decision-making is one that's been studied in other disciplines. And so two excellent books that I recommend are Farsighted and Decisive, that talk about some of the common problems that we might have with decision-making. So one, narrow framing, looking at limited choices. So that's the single mousetrap on the shelf where we're making a binary decision, when in reality, we should have a richer set of possibilities to consider. Confirmation bias happens when we are latched onto a solution too early, and so we stop being open to other possibilities. We could also think too short term, so not include thinking about long-term consequences. And a lot of times we're overconfident that we have the right model, that nothing's going to go wrong. And so we don't build in sufficient uncertainty about how things are going to go. And then lastly, team dynamics. If we're on a team, I think we're all familiar with the case where the loudest voice has won and not the best science. And so we want to have strategies in space to mitigate against that. So here is the DEMREX process, and I've illustrated it with choosing a design. That's the most common decision-making process that I've been associated with working on teams. So in the define stage, we're figuring out what's important. What are we prioritizing? And we're getting sort of the class of designs that we're going to have available to choose between. In the measure stage, we're translating those priorities into quantitative criteria, and we're making sure that we can assess that criteria for the designs that we're going to be looking at. The reduce stage is a little bit of prioritizing of those objectives to not overwhelm ourselves with too many objectives, but a Pareto front can also be very important here to eliminate designs that are non-contenders or implausible. The heart of the process, where we switch from objectively gathering the right collection of designs to figuring out how to evaluate those trade-offs, that's where we sort of need some tools and graphics to be able to negotiate that relative emphasis of our priorities. And then ultimately we get to run exactly one experiment, or usually just choose one solution. And so we need to feel confident in that solution and be able to defend it to our bosses. We also, Lou and I wrote a paper on the graphics to facilitate this process. And it's a paper with discussion. And so what we did was look at each of these steps and come up with some things to prioritize in the graphics at each stage that allows us to be able to package the message and to guide the discussion in a productive way. Lastly, I think Pete Parker and Lou and I talked about collaboration strategies. And so last year in this FTC webinar series, I talked about that. And so there's a link to that talk. And then it all fits under this umbrella of statistical engineering. And I would encourage you to think about a free membership for an individual for joining ICEA. And ICEA is also hosting a workshop November 18th and 19th. So I'll give a plug for that, that I think is worth considering. Some just great discussion on the practice of statistics. So in conclusion, there were several needs that I identified that helped us transition as statisticians from the sales clerk behind the counter, finding the right product on the shelf, to more that interior design working collaboratively on the team. We needed the ability to generate multiple designs that allowed for the comparisons. We needed the right tools to make specific and meaningful comparisons based on the goals of that experiment. I think sequential design of experiments opens doors for us about how to learn from our early data and pivot based on what we've learned so that we collect strategically in the next step. And then lastly, in order for our voices to be heard, we need human skills. And so a lot of people call these soft skills. Human skills to me is a much better label for this, and it's a term coined by Simon Sinek. And if we're going to lead and be part of teams, collaborative teams, making sure we feel confident in our human skills is very important. I'll finish with a very optimistic note. I think these are super exciting times in statistics. So many new areas emerging where we can make important contributions. And I think new ideas to help improve problem solving and decision making are a key area for us to be focusing on. But in general, letting the needs of our science and engineering collaborators guide us in the direction for where innovation is needed, that feels like a way to have a substantial impact. So in the slides that will be available on the website, I've included some references for each of the topics that I've talked about here, just to fill in some details that I had to zoom by in the talk today. So I'll stop there and I'm happy to answer any questions.
Thanks so much, Christine, for that awesome talk. Yeah, I learned a lot. I will go ahead and open it up for questions. If you want to use the Q&A button, you can type in a question there for Christine. I guess while we're waiting, one just came in. So it says, if you're in a situation where you're getting bombarded with requests because of high demand for services, how do you get out of the sales clerk model? Just answered because of the lack of time and shift to the interior design model.
So that's a really good question. And that's probably a question for managers as much as individual statisticians. So I guess I'm more of a fan of building deeper relationships and sort of getting some expertise in particular areas. And so the long-term goal certainly is to develop sort of a place on teams long-term. If the problem is really a shortage of time, it's going to be a tough struggle to get out of that sales clerk mode. But I think that's a moment to sort of talk to a manager and say, we're giving basic solutions here. Is there a way that we can just focus on a smaller set of problems, but then really have a big impact with those? And so there's some triage needed to identify what are the key problems and which ones can you maybe run a short course and give people basic skills so that they can look after some of the simpler questions that frees you up to work on some of the more interesting high impact problems. So time is sort of the most valuable commodity we have, but I think the quality of solutions and the opportunity for higher impact, that should be something that drives us to sort of get involved in the right problems and not just work on every problem that comes through the door.
Okay, yeah, another question here. It says, do you have an opinion on using definitive screening designs to begin your sequential design approach?
So I think so to me, definitive screening designs do a really nice job of targeting the ability to figure out which factors are important, but they also have built into them that ability to check whether the assumptions of the model are looking good. And so I think they're a nice, well-rounded design in terms of covering several of the more common objectives that we have for that first experiment. I think there's a big fork in the road of, do we want to do space filling or something model based? That's probably comes before deciding on a particular design. And I do feel like a lot of times where there are assumptions that are built into going with a model based design, sort of continuous smooth surfaces. And so we need to think carefully about whether that's an appropriate assumption. And if it's not, space filling might be a better way to start. But if we're comfortable with a smooth, continuous surface, then I think a definitive screening design is very natural in terms of tackling a couple of common objectives in that first stage. So great designs.
Thanks. Yeah, the next one from John Lewis. He's asking if you have a white paper on sequential DOE.
Yes. So I think I'm going to jump back to sharing my screen, if that's all right. And so, oops, there we go. So a couple of papers. I think the first one probably is very good in terms of just sort of the context of the problem, sort of the nuts and bolts of how the augmentation can work. And just that philosophy of breaking things into manageable parts and tackling them one piece at a time, I think that can feel very helpful for sort of the manager level introduction. I think why not sequential DOEs might be a good way to just build some context for like why this can be an advantageous approach.
Great. And just to follow up on that one, is your LANL email still good or?
It is.
Okay.
But I think on here, I've also given my Gmail account. I'm happy to respond to any questions there as well.
Awesome. Okay, the next question, saying from a settler, not an explorer, what are some tools, new tools or innovative ideas you'd like to see more settlers adapting?
So I think the whole space of statistical engineering is really all about that settler. So if the analogy, I think, of an explorer is probably someone who's focused more on statistical science, so developing new things, and statistical engineering focuses more on how to actually use those tools. And so I think there's a real, so if I think about how I learned what I know about the engineering part of things, it was all through experience and from mentors, of course. And so I think statistical engineering focuses on how do I choose the right tool? How do I build a sequence of understanding the problem, to collecting the right data, to getting all the way through the analysis, and then sharing what comes out of that analysis with a manager or the person who's actually going to be acting on that decision. And so I think there is a wealth of tools, a lot of them borrowing from other disciplines that have thought about engineering and problem solving. And so I'm going to share my screen again. I will give a plug to the engineering handbook. So I think, let's see, there we go. So ICEA has just, Lynn Hare was the lead editor on the statistical engineering handbook that has just come out. And so it is filled with a wealth of tools that many of us may have intuition about, but have not thought about in a formal sense, about how to do that problem solving and decision making part of things, about choosing tools and putting them together to make sure that we're focused on the right solution to the right problem. And so that to me is a great starting point if you're looking to build the settler part of things, it will really help guide how to work with the tools that are already out there, which are very comprehensive, and turn them into good solutions for your particular problem.
Okay, thanks. Yeah, I think we have time for one other question. So if we already have the Pareto Front with multiple designs, how to ensure the best choice of these designs? Or do we just assume these multiple designs that they have the equal weights?
So very good question. I think as statisticians, a lot of times we think very objectively. We think there's sort of a right answer. And I think the beauty of the Pareto Front is that it's helping us explore that subjective space. So thinking about the input response example that I showed, for someone who only cares about space filling in the input space, the right answer might be that sort of bottom right-hand corner design. But for someone else, where they want to get sort of adequate performance on both of those criteria, then we want to shift somewhere to the middle of the curve, or sort of towards somewhere along that curve. And so I think it's very helpful for us to remember the distinction between objective, 2 + 2 is 4, and subjective, which is I prefer that we spend more of our budget in this early stage, and we're going to have to find ways of saving money later. So there is no right answer to that second question. We just have to negotiate with our team about what seems like the best fit for our commonly shared priorities. And for statisticians, I think we have to get comfortable with that being the right approach, instead of, yep, there's a right answer, I just have to find it. Because in these cases where we're balancing multiple objectives, how I value cost relative to performance is probably a bit different than you. And we have to have a meeting of the minds to come up with something we're both happy with.
Okay, well, thank you so much. Again, congratulations. And I think I can speak for all of us to say thanks for this awesome talk, and congratulations on your award.
Great. And thanks for the opportunity. And it's indeed an honor. Thank you.